Welcome to MS 100 lessons, and in this lesson I will be focusing on Newton's second law analysis. So looking at the outcomes, I will first state out the Newton's second law in words, and we will have an analysis of the formula F net equals to ma. So for me to introduce this topic, I will introduce it using an example. So let's say we have an object of mass 5 kg. Okay, and this object is resting on a horizontal surface. Okay, so the surface, let's say it is smooth, and by this we mean there is no friction, right? So the surface is frictionless. Okay, so since the object is resting on that surface, it means the velocity of that object is equals to 0 meters per second. So the object is not moving. All right, so according to Newton's first law, this object will remain at rest, right? Because the velocity is equal to 0. It will remain at rest unless there is a net force applied on this object, right? So if the object was moving with a constant velocity in a straight line, then it would continue to move in that straight line with a constant velocity unless a net force is applied on the object. But for this example, we are saying the object is stationary, right? And the velocity is equal to 0. So now, what conclusion can we have from the term rest? So if an object is at rest, it is not moving. And by conclusion, that is because the net force acting on that object is equal to 0 in each and every direction. So if we were to draw a free body diagram, a simple free body diagram for this object, we would have normal force and the gravitational force of the object, right? And in this case, the normal force is equal to the gravitational force. Therefore, the net force is equal to 0 in the y direction. And there is no force acting in the x direction. Therefore, the net force is equal to 0 newtons in the x direction. So the net force acting on this object is equal to 0 in each and every direction, right? So what happens if we try to apply two forces at the same time on this object, right? For example, we apply a force of 50 newtons to the right and a force of 50 newtons to the left, assuming we are applying these forces at the same time, right? So what will happen to the object? If we try to draw a free body diagram for this object, we'd still have the gravitational force and the normal force, right? But now we have an applied force 50 newtons to the right and an applied force 50 newtons to the left, right? So if you try to calculate the net force on this object, the net force in the y direction, you have two forces, which is the normal force and the gravitational force, right? But these two, in this case, normal force is equal to the gravitational force. Therefore, the net force in the y direction is equal to 0 newtons, right? So let's check the net force in the x direction. So if you try to calculate the net force in the x direction, we have two forces, which is an applied force of 50 newtons to the right and an applied force of 50 newtons to the left, right? What will happen to the object, or what will be the net force? Since the magnitude is the same and they're acting in opposite directions, this is positive 50 newtons, provided that you are choosing right as positive, and this is negative 50 newtons, provided that you're choosing left as positive, right? Then that would be 50, which is the positive one, plus negative 50, which is the negative one, right? And still your F net is equals to 0. So what will happen to the object when you apply these two forces of 50 newtons at the same time? So the conclusion is nothing will happen to the object, right? The object will remain at rest. The object will not move at all, right? The object will remain at rest. And why is that so? And that is because the net force is equal to 0. An object will remain at rest, right? But unless a net force acts on the object, we had two forces acting on the objects, right? But nothing happened on the object. Why? Because the net force is equals to 0. Okay, so now the object will not move because you're applying a force on that object, but the object will move because you are applying a net force on that object. Because with this scenario, we were applying two forces at the same time in opposite directions in such a way that the net force acting on this object is equals to 0. Nothing happened to the object, right? So what happens if we apply a force of, say, 80 newtons now? We apply force of 80 newtons to the right, and we still maintain a force of 50 newtons to the left, right? We apply these forces at the same time. So let's see what will happen, right? Now, with this scenario, if we try to draw a free body diagram, we have our FG going downwards, and we have our normal force, right? And we have our applied force, which is 80 newtons, and we have our applied force, which is 50 newtons to the left. Okay, so now let's try and calculate the net force acting on this object. So looking at the net force in the y direction, right, you have two forces, which is the normal force and Fg going downwards if downward is negative. But then now in this situation, the normal force is equal to the gravitational force. Therefore, your net force will be equal to 0. Okay, so your net force is equal to 0 in the y direction. Still nothing will happen in the y direction. So let's check the net force in the x direction. If you try to calculate the net force in the x direction, you have two forces. You have the applied force, which is the 18 newtons, and you have the applied force, which is the 50 newtons, right? So the net force is equal to 80 minus 50, and we get 30 newtons, right, to the right. So now we do have a net force acting on the object. So the net force is no longer 0. So now what will happen to the object, right? Because we concluded that if the two forces were equal and the net force is equal to 0, we concluded nothing will happen to the object, right? It will remain at rest. But now we are applying two forces which are not equal in opposite direction, and we have a net force of 30 newtons to the right. So now what will happen to the object? So our conclusion for this scenario is that the object will accelerate, right? And this object will accelerate in the direction of the net force, because the net force is 30 newtons to the right. So that is the direction of the net force. And we are saying the object will accelerate in that direction. So it means that object will accelerate to the right because the net force is also being applied to the right. Okay, so now we can see that when a net force is applied, the object must accelerate. When there is a net force, the object will accelerate. But if there is no net force, the net force is equal to 0, then the object will not accelerate. Okay, it will remain at rest, or it will remain moving with a constant velocity in a straight line if it was moving with a constant velocity, unless a net force acts on the object. Now the net force is acting on the object. What will happen to the object? The object will accelerate in the direction of that net force. Okay, so that is conclusion number 1 from this scenario whereby we apply unbalanced forces. But now we want to look at that acceleration, right? We want to check the magnitude of the acceleration. We have already determined the direction of the acceleration, that the acceleration will be in the direction of the net force. Okay, so now we want to check the magnitude of that acceleration. What affects the magnitude of the acceleration? So assuming that we have applied a force of 80 newtons to the right and a force of 50 newtons to the left, our net force was 30 newtons to the right. Okay, and then that 30 newtons to the right gave an acceleration of some magnitude in that direction, which is to the right. Okay, so we have a net force of 30 newtons, and that net force of 30 newtons will give rise to a certain amount of acceleration. Okay, so for another scenario, say we had a force of 200. For example, we had a force of 200 newtons to the right. So our net force in the x direction, if we were to calculate our net force in the x direction, then it would have been 200, which is positive, minus 50, and that is 150 newtons to the right. Okay, now we would have a net force of 150 to the right. So that net force of 150 to the right would give also an acceleration of that object. But question is, will the acceleration due to the 30 newtons be the same as the acceleration due to the 150 newtons? The answer is no. The magnitude of the acceleration would be different. Okay, so which one is greater and which one is smaller? So looking at the two values, you have a net force of 30 newtons, right? That would give an acceleration which is lower compared to the acceleration which is given by the 150 newtons, which is going to be a higher acceleration, okay, or a large acceleration. So it means the greater the net force that you apply, right, the greater the acceleration that you would get. The smaller the net force that you apply, the smaller the acceleration that you will get. Okay, so very important here, I want you to see that this object is accelerating due to a net force. Okay, but it is not accelerating because we applied a force. No, with this first scenario we applied two forces, which is 50 newtons, 50 newtons. The net force was 0, so nothing happened, right? But the moment you apply a net force, that is when an object will accelerate, and the magnitude of that acceleration depends on that net force. If you apply a greater net force, you would get a greater acceleration. If you apply a smaller net force, you will get a lower acceleration, right? So the conclusion is that the magnitude of the acceleration of that object is directly proportional to the net force that you are applying. The greater the net force, the greater the acceleration. So the mathematical relationship that we can conclude from this statement is that the acceleration, or the magnitude of the acceleration, is directly proportional to the net force being applied. Okay, so number 2, the magnitude of that acceleration is also dependent on the mass of the object. So number 1, it's dependent on the magnitude of the net force that you're applying. And then number 2, it is also dependent on the mass of the object. So assuming you have two different objects, right? You have a mass of 5 kg and you have a mass of 100 kg. So if we were to apply the same amount of net force on both objects, say for example, we apply a net force of 30 newtons to the right on both objects. So we want to see which object will experience a greater acceleration, right? And from these two, you can see that it is a bit difficult to accelerate an object which is heavier or an object that has a bigger mass compared to an object that has a smaller mass, right? Using the same amount of net force. So it would be easier to accelerate an object of a smaller mass, right? And it would be difficult to accelerate an object of greater mass. So it means that if you have a smaller amount of mass, then it means the acceleration would be greater. So the acceleration, if the mass is greater, then the acceleration would be lower, okay? And if the mass is lower, the acceleration would be greater. So we can conclude that the magnitude of that acceleration is inversely proportional to the mass of the object, right? So that is the two factors that that the acceleration depends on, which is the net force and the mass of the object. So we can simply say the acceleration is directly proportional to the net force. The greater the net force, the greater the acceleration. The lower the net force, the lower the acceleration. And it is inversely proportional to the mass of the object. The greater the mass of the object, the lower the acceleration. The lower the mass of the object, the greater the acceleration, right? So we can also write this like that. The net force is directly proportional to the product of the mass and the acceleration, right? So now we want to remove this this proportion sign with the proportionality constant, and then we insert an equal sign, right? So if we want to do that, we say the net force is equal to, instead of using that proportionality sign, we say it's equals to a proportionality constant multiplied by MA, right? But for our derivation, for this derivation, we use K is equal to 1, right? And why do we use K equals to 1? Because for this derivation, we are saying the F net that is applied on this object is 1 Newton, the mass of that object is 1 kg, and the acceleration is equal to 1 meter per second squared, right? If you substitute all these values on this equation, you get K is equal to 1. So now, if K is equal to 1, right, that is the same as F net is equal to MA. So this is Newton's second law in terms of an equation. The net force that is applied on an object is equal to the mass multiplied by the acceleration of that object. So now we can go back to the first learning outcome of the lesson, which is stating Newton's second law of motion inwards, right? So from the scenario that we explained here, we explained that when you apply a net force on an object, right, that object will accelerate in the direction of the net force, right? That is part number one. And part number two, we talked about the magnitude of the acceleration. That acceleration is directly proportional to the net force, right? And that acceleration is inversely proportional to the mass of the object. So now we can state Newton's second law of motion inwards. Newton's second law of motion inwards, it states that when a net force is applied on an object. So that is the first part. And the most important thing that you have to note is that we said the net force, right? Not when a force, when the net force is applied on that object. So what happens if you apply a net force on that object? The object will accelerate. And this object will accelerate in the direction of the net force. Okay? And most importantly, the object will accelerate, not the object will move. The object will accelerate in the direction of the net force, right? So now we insert the second part of this definition, which is the proportionality part, which is the acceleration is directly proportional to the net force, and that acceleration is inversely proportional to the mass of the object, right? So we say the acceleration is directly proportional to the net force. So meaning the larger the net force, the larger the acceleration. The smaller the net force, the smaller the acceleration, right? The acceleration is directly proportional to the net force, and this acceleration is inversely proportional to the mass of the object. So the net force is directly proportional to the net force and inversely proportional to the mass of the object, right? That is Newton's second law in words, which is F net is equal to ma.